I know that one thing you love is the idea of Einstein and time being different and all that. They figured all of this out around like 1908. It was more than 100 years ago. And, we don't really even have a better thing yet. They figured out that time isn't the way that we experience it just by really simple, brilliant thought processes, observations 100 and some years ago, 100 and a little more than 120 years ago. Yeah, incredible.
The idea that the faster you go, the slower time is so hard to wrap one's head around. And one of the things that I heard you were talking about GPS satellites. Mm-hmm. And you were saying that GPS satellites, because they're going about, what are they going, like 20,000 miles an hour or something like that?
So actually, if we want to break this down a little bit, there are a couple different effects about time. And one of the things that NASA does is calibrates the GPS satellites and the signal coming. And you wouldn't, I think I heard that, within a day, if we didn't take into account the time difference these things are in, that we'd be about 6 miles off. In a single day.
That's crazy.
Oh, yeah. No, it's a big deal.
That's so crazy.
Yeah.
That's so crazy, and that's just above us.
Time really is something. This is not a theory. Time is variable depending on how fast you're going and also how far off the Earth's surface you are, or how far away from a big gravity body you are. In the case of the GPS satellites, there's two things going on, and it's kind of fun because it's actually the reverse for the astronauts. So I want to break this down. This is really fun. Okay, we have clocks that are so accurate that if you move about 2 feet above where, if we had a clock on this desk, and then if we moved it up about 2 feet, we could actually detect time flowing differently because you're just that far away from the Earth's gravity, just 2 feet. Your head and your feet, we spend most of our lives, say, standing up, are actually going through time at slightly different rates. The farther away you are from a gravitational source, you probably liked movies like Interstellar, right, mm-hmm. with Matthew McConaughey. Remember the big black hole? Mm-hmm. And the closer they get to the big black hole, the slower time goes. That's not a theory. That's something we can actually measure with clocks. And a black hole has so much gravity, it does it a lot more dramatically. But it's happening right in this room. Seriously, your head is in a different time frame than your feet right now.
That's nuts.
Yeah. And it's measurable. You need extremely accurate clocks. But in the case of the GPS satellites are in what we call a medium orbit. They're not as far away as the geostationary satellites, but they're not actually going that fast. They're only going about 9,000 miles an hour around the Earth. The astronauts in the space station, by the way, are going much faster. They're going more, let's say, approximately 20,000 miles an hour. So the GPS satellites are going a little slower. And 8,000 miles an hour is a lot, and that does slow your time down. But the bigger effect for GPS satellites is how far away from the Earth they are.
Wow.
We're actually going slower in time than they are because we're closer to the Earth's gravity. And they're so far away, they're actually going a little faster than we are in time. Now, they're also slowed down by their fast velocity. The faster you go, the slower your time goes. But people don't realize there's another factor, and that's how far away you are from gravity. For the astronauts are closer to the Earth, right? So they're actually not so far away as the satellites, and they're going much faster. So for the astronauts, it's the motion, it's the time dilation from the motion that's a bigger effect. If you are on the space station for a year, you come back about 1/100th of a second younger than you should be. And obviously that's not a big deal, but it's easily measurable.
Wow.
And in the case of the satellites, you wouldn't get the right location. The data wouldn't be right unless we take into account two things: how fast they're going. The closer to the speed of light you go, the slower time goes, but also how far away from the gravitational pull of the Earth they are. The closer you are into gravity, the slower time goes.
I think the weirdest thing that I've ever heard anybody say is that all time exists currently.
That's Einstein. That goes back 120 years.
That's such a bizarre thought.
We don't know if it's true, but it's, Einstein really thought there wasn't much of a way around it because he said, okay, well, if everything is going at different velocities compared to everything else, right? It's a great question a kid can ask. How fast am I going through space? And the Earth, if you're on the equator of the Earth, that goes around at about 1,000 miles an hour, and then, we go around the sun at about 67,000 miles an hour in our orbit. The sun's going around the galaxy about 500,000 miles an hour around the galaxy. The galaxy is going towards a galactic cluster at more than 1 million miles an hour. But how fast are we going really? And the only thing you can measure is how fast are you going relative to something else. There's no answer. How fast am I going? Well, I mean, am I still or am I actually traveling close to the speed of light right now? I don't know. So Einstein said the only way he could really think about how that would work is if the universe was just one big thing. All of time and space exists in a big whole thing. There's only one now. Einstein famously said, the past, present, and future are, persistently annoying illusions. Now, again, do we know this to be true? At the moment, we don't have any better physics, and I doubt the physics will get any less weird than that. But I mean, that's sort of the way modern physics thinks the universe may be, is a big whole thing that started from beginning to end and is all now-ish.
But if that's the case, so subjectively we can measure things. We can measure time. But what are we measuring? If it's, are we making artificial time constraints? Are we doing it ourselves? When we create a clock, we create a watch, and the watch is 24 hours a day. It's running. What is it measuring?
Yeah,
right.
That is exactly the question Albert Einstein asked. That is a deep, excellent question. And so that was the problem. I mean, in a famous thought experiment, Einstein made a clock by setting up two mirrors and having light bounce between the two mirrors. And that was the tick of the clock. Tick, 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 tick. And the problem was that that's how he started thinking about the speed of light, is that if you had this thing in a spaceship that was going a huge fraction of the speed of light, then a person standing watching it go by would actually watch the light kind of trace out a pattern like this. Because it's actually ticking between the mirrors, but the mirrors are moving along. And so you see the light make this sort of bouncy movement. And that means it's actually traveled farther than the person on the ground who thinks that the mirrors are just sort of, the light is making just a straight up and down line from mirror to mirror. That question that you asked is what it completely revolutionized physics. Everything fell apart when people said, how do you even measure time? What does it mean to make a clock? What are we measuring?
I still don't understand what we're measuring.
Oh, Lord. Yeah.
I get it. I don't
know if I have an answer for you. I don't think anybody does. But here's the deal. So the clock in Einstein's experiment, so the clock has, two mirrors and there's light bouncing between it. And then and that's the distance that it travels in one tick.
Right.
But now you put that clock on a spaceship, and the spaceship's going really fast. And as it goes by, you see that clock, as it streams by you really fast, you see the light make this motion. And this line is actually longer than that line. This line, if you measure it, that's actually a longer line that I drew than the original one between just the two mirrors, because now it's at an angle. And this is what made Einstein say, time has to change. If anything moves, the tick of a clock changes. However you measure time, whatever time is, whether you measure it with a bouncing clock or whether you measure it with a vibrating atom like we do in the Bureau of Standards, or whether you measure it with a spring that's slowly unwinding in a wristwatch, anything you can do to measure one moment to the next changes when motion is involved. There's no way to get around it. It's not just the measurement. It's time itself is changing. Any way we have to measure this thing we call time. And I have to tell you, Joe, I don't think we have an answer to what time is. What are we measuring? I think right there, I think you're asking for the next revolution in physics that we don't have yet. I really mean that.
So when we're measuring time currently, like when I look down at my watch, I'm measuring time in this particular space. Like where I am, what altitude I'm at,
right,
how fast I'm moving, and the watch just does a reasonable job of calculating all that.
And that's you. I mean, that's what you see here, sitting still with your watch, looking at it.
Right.
If someone's flying by at close to the speed of light, they won't see you measure time the same way. Yeah.